The irrational numbers is the black. Does that make sense? It's everywhere, but you can't even like point it out. You can't point out the black, but it's there, right? The irrational numbers are in here. It's the black, and the stars are the fractions. So by me closing my eyes and doing that, that's equivalent to me asking you to point into the sky, open your eyes, and the chances that you're actually pointing directly at a star. You have to make a concerted effort, right? You actually would have to make a concerted effort to look at a star. You have to aim for it. If you just randomly close your eyes and open, the chance that you're looking directly at a star is essentially zero. Does that make sense to you? If you don't like it, you don't have to like it. It's called measure theory, and that's what our entire number system and all of our mathematics is based upon. So, you know, it is what it is. There's nothing we can really do to change that. Yes?
So does that mean that there's a lot more irrational numbers?
Yes, that means that the irrational numbers are uncountable and that the rational ones are. So there is a way to march your way across here, touching every fraction as you go. There is a way to march through the fractions like lily pads across this number line. But it's impossible to do that with the irrational numbers. You cannot jump around. There's so many more of them. They're both infinite, but there's just this other type of infinity that makes countable look like nothing. Anyway, okay, that's random.
Would you consider fractions countable?
Yes.
Even though they can get infinitely smaller?
But I can actually list them all out and cover all of them. Like there's a way for me to go through all the fractions and never miss any. I can never get to the end of the list, but I could just walk my way through.
Wait. So doesn't that mean that infinitely small fractions are the uncountable numbers?
No. Like an infinitely small fraction would be like 1 over a million, right? That's really small.
Yeah.
What I'm saying is I could start listing out fractions right now. Just the way I could say 1, 2, 3, 4. I can start listing out the fractions like that, and I would eventually get to any fraction that exists. I can just speak my way through all the fractions and never miss one. But it's impossible for me to do that with the irrational numbers. I cannot start listing them out in any order. If I try to, as soon as I say the first one, I try to go to the second one, I've already missed an infinite number of them. And there's no way, if I go back, I missed an infinite number going back. So there's just no fluid way through them. I don't know. It's an abstract idea. I mean, you don't even get into measure theory until you're a junior and you're a math major and you're studying this, right? It's not as bad as it sounds. It's actually pretty enjoyable. It sounds horrible? You know.
I mean, is there like an actual percentage that you could actually, per se, shoot directly at a star?
Well, a star, yeah, I mean, that's an analogy. I mean, that's the best analogy I can give. I mean, there's nothing else that I can really say that explains it better than that, I think. But, okay, how are we doing? 40 minutes? That was just a little mental break. Did that not feel like a mental break? Sorry. 30 minutes, yeah, everyone's ready to go. Sorry, we got a little more. Continuity. So we're taking a step backwards in the book, but in terms of concepts, this is not weird for us to go backwards. Continuity. So I'm gonna give you the definition of continuity here. All right, I'm going to, but I think I just want to show you a picture first. Look at that graph. If I start drawing this graph, can I draw it without picking up my pencil? Nope, right there I've got to pick up my pencil and continue, right? This is not continuous at 2. Everywhere else I can just draw it without picking up my pencil. If I ever have to pick up my pencil, then I fail to be continuous at that point. So this function is not, the question is this function continuous at 2? No. It's continuous everywhere else except at 2. Is this function continuous at 2? No. Do I still have to pick up my pencil? Yeah, I have to go like that, and then yeah, I can fill that dot in, but then I have to continue. That's not continuous at 2. Is that function continuous at 2? Yes. I can draw it. Right? Okay. So let's see if we can't relate this idea to limits. Okay, I want you to just look at what's happening at 2. Go back to last class. Is this function defined at 2? No, right? It's undefined at 2. Does the limit exist at 2?
Yes.
Does the limit exist? I see some. Yes, what's the limit as x approaches 2 here? 8. Y'all see that? From both sides, it's 8, right? So in this picture, f of 2 is undefined, but the limit as x approaches 2 is 8. And it's not continuous, right? This one, is this function defined at 2? Yes. Does the limit exist at 2? Yes. Are they the same? No. Is that function defined at 2?
Yes.
Is the limit exist at 2?
Yes.
Are they the same?
Yes.
Is it continuous at 2?
Yes.
That's the condition you need for continuity. You need at that point to be defined, and that your function comes in from both sides to that point. If you have that, you have continuity. Do we have the limit existing? Do we have it defined? This one, no. So it can't be continuous there, right? I'm trying to get you to see visually what the idea of continuity is. This one, with the limits exist, the function's defined, they're just not the same, so we're not continuous. For continuity, you got to have you have to have both of those things line up. You have to have the limit exist, and where we're headed is actually filled in right there. It's defined to be that.
All three of them have to be lined up.
Exactly. So to be continuous, I'm going to write down, to be continuous at x equals a, we need this to be true. See if this makes sense. We need the limit as x approaches a of the function. Right? So we need this limit to exist, and we need it to be equal to, what did we say? This limit exists, right? And what do we need it to be equal to? The function's value at 2, which is 8, right? So we need this limit to be equal to the function's value at that point A. See, this is like from last class. This is the calculus, right? This is the calculus, this idea of a limit. The calculus part has to be equal to the algebra part. What's happening at the point has to be equal to where we're headed from both sides. If that lines up, if these are equal, then we would say it's continuous there. That's the definition of continuity. So I'll show it to you in the notes because it's not as pretty when you look at it in the notes. There it is. A function f is said to be continuous at x equals a if the limit as x approaches a of f of x equals f of a. That's that. That has to equal the point. If that happens, we're continuous there. Is that continuous at 2? No. Why? Tell me why this is not continuous at 2. Because the limit isn't the same, right? The limit isn't the same from both sides, which means this side is what? Does not exist, right? And this side is what? 8. And does not exist, doesn't equal 8. So that's why that's not continuous there. Is that continuous at 2? Does the limit exist?
Yes.
What is it? Is that equal to the function's value there? No, because that's 5. So that's discontinuous.
What if the dot wasn't there?
Oh, good question. If the dot wasn't there, then this would be what? The limit would be infinity, and this side would be undefined. It would be undefined, right? So infinity doesn't equal undefined. That one?
No.
Why does this one fail to be continuous here?
Because it's open.
It's open, which means this side, the limit exists, right? But this side is undefined, right? We don't have anything filled in there. All right, that kind of makes sense to you? All right. Let me show you a picture of this. Is that function continuous at 2? No, right? Why is, like, what is the thing that's really causing the problem here? The jump, right? That little jump? Okay, this left side, that limit's coming in, and it's actually going to a point, right? But it's this right side that I wish it was like up here, right? I wish that right side came in, and then they would both come into the same place. This function is what we consider left continuous at 2. Left continuous. Does that make sense to you, just the verbiage there? If I go to 2, from the left, does the limit exist? Yes. Is it headed to the same point at 2? Yes. Then that is left continuous, but it is not right continuous. Okay, so left continuity is a weaker condition. It only requires that you look from one side. Yeah, because the closed dot. As we come in from the left, we're headed to the actual closed dot. So this would be left continuous. This is not right continuous because when we come in from the right, notice it's headed to this open circle. So it's not continuous, right continuous.
So the circle was closed, be right continuous, and then the circle was open. Oh.
There you go. So this is right continuous at 2 and not, not left continuous. The only difference now is I move that dot from here to here. Yes?
What if both the points are close?
Then it's not a function, right? So then it would fail to be a function, which means you can't talk about this anyway, right? Because then you would fail the vertical line test. Good question. What if they were both open?
None.
Then it's neither. You're not left or right continuous. You actually have to have a solid dot there to even talk about continuity. We could kind of rethink this. It's like I can draw this without picking up my pencil from the left, right? But if I draw it this way from the right, right there at that hole, I have to pick up my pencil. And then on this one, it's the other way around. I could draw it from the right, fill in that dot, I'm done. It's right continuous, but if I do it from the left, I'm going to have an open circle there. Now, look at that. That is a function that I have defined on a closed interval from 1 to 3. The question is that function continuous everywhere in there? So if you go to any point here, go to any point on this graph, is it continuous there?
Yes.
Yeah. Is it continuous here? Yes? Here? Yeah? Here? Here? Right? It's continuous everywhere on the inside. Now what about here? Is it continuous there? It's right continuous, right? It's right continuous there? Because as you come in from the right, it's continuous. How about this point? You're left continuous. So when we talk about continuity on an interval, I'm going to scroll back up. A function is said to be continuous on an interval if it is continuous at every point in the interval. So everywhere inside you have to be continuous, like from both sides. But when you get to the left endpoint, you only need to be right continuous. And when you get to the right endpoint, you only need to be left continuous. And then you can say it's continuous on the closed interval. So like I said when I started this, the idea of continuity is the idea that you can draw a function without picking up your pencil. That's like the layman's way of saying it. This theorem is a theorem that allows us to talk about continuous functions and how we can combine them together. So like if I take a continuous function and put it together with another continuous function, add or subtract them, it stays continuous. Like if I can draw this one without picking up my pencil, draw this one without picking up my pencil, add the two functions, that new drawing you should be able to draw without picking up your pencil. And that works for pretty much all the operations. If you multiply by a number, Scale it, it still stays continuous. If you multiply two continuous functions, it should still be continuous. If you divide them, it should be continuous, so long as the denominator is never 0. If the denominator is 0, you're going to cause a discontinuity because you'll have an asymptote or something. So what functions that you know in your life that you've studied are continuous? Almost all of them. Polynomials, remember in college algebra, the ones that look like roller coasters? You drew those without picking up your pencil, right? Rational functions, those are the ones that had all the vertical asymptotes, right? Those are continuous on their domains. So other than the vertical asymptotes, right? In college algebra, you have like rational functions that look like this, maybe like this, right? These functions are not continuous everywhere because they have vertical asymptotes, but everywhere else, right? Like anywhere in here, you draw without picking up your pencil. Sine curves, trig, right? Sine, cosine, tangent, all of those, as long as you're in the domain, they're nice. They're nice. You can draw them without picking up your pencil. Exponential and logs, same way. So I have like pictures. We don't have to go through these. Polynomials, rational functions. See, wherever the blue is nice, right? Of course, we have bad spots here and here, but other than there, everything is a nice curve. No weird jumps or breaks. Trig, exponential, right? Log. The last theorem here says that if you take a continuous function and you plug it into a continuous function, like composition, f of g of x, that sort of thing, that you maintain continuity that way. So here's an example. This is sine of x squared minus x. So the inside is a parabola, x squared minus x. Parabolas are continuous. And I'm plugging it into a sine function, which is continuous. So the composition of those two, as you can see here, is something that can be drawn without picking up my pencil. And I can do that for all these different, there's a bunch of other ones I have here. Here's a composition of two continuous functions. Here's another one. Here's another one. Another one, right? All right, how are we doing on time? Intermediate value theorem. I'm debating here. Yeah, I really don't. I want to stop and say, let's call it, a week and leave it. We need the time, trust me. Later on in this class, you will be begging for more time to get through some stuff. So let's just grind the rest of this out. Do y'all feel like I'll have like a basic idea of what continuity is in terms of visual? Yes? All right, now we get to a very important theorem in math called the intermediate value theorem. And this theorem is going to seem kind of like duh, like that makes sense, like why is this so important? But it's something that has to be proven, and so we can't take it to always be true. Here's the way the theorem works. All right, I have a picture for you. Let's say we have a function. You see this function here? Is that a continuous function? Yes, it's continuous, right? You can see it, draw it without picking up your pencil. Intermediate value theorem says, all right, let's say we take that function and we restrict it to a closed interval, right? Let's just look at it between here and here. So I've cut it off, all right? Now what I want you to do is I want you to consider the two endpoints of this function. The left endpoint has a y value of negative 12, and the right endpoint has a value of 13, right? So see that? It goes from negative 12 to 13. It does some other stuff in between, goes up and down and back up, but those are my two endpoint values. Yeah? Okay. 13 and negative 12. Somebody now give me any number you want between 13 and negative 12. 5 is the first one I heard. 5, right? So 5, I'm going to try and go to 5. Where's 5? Somewhere around there, okay? There's 5. Do you all agree, everyone, that 5 is between these two? The intermediate value theorem says that guaranteed 100%, that function, somewhere on that function, it achieves that value of 5. somewhere on that function, it actually is happening right here at 4.49. If I plug 4.49 into that function, it hits 5. Okay? Do you see that the number 5 was an intermediate value between these two endpoints? The intermediate value theorem says if you try and pick any number between these two values, any intermediate value, there is some x coordinate on the function that will get mapped to the number you picked. I want someone to pick another one for me. All right, what was the second one I heard? 2. Okay, so if I pick 2, right, so I pick 2 instead. There. Guaranteed, because it's a continuous function, there's got to be some x value, in this case 4.22, that when I plug it into the function, it's going to achieve that too. And I could do this all day long. I do it for any value you give me. I'm going to be able to find values which will spit that out.
What if there's one of the values where the line teaches?
More than once, then you would have multiple values. So let me read the theorem to you. Suppose f is continuous on a closed interval. So you've got a closed interval, it's continuous. And that the two endpoints, the high point, the low point, or the other way around, as long as they're not the same, as long as we've got space between them, like it was what, 13 and negative 12? As long as we've got the two endpoints being different values, then we can now choose any number we want between those two endpoint values. N, it was 5 and then 2, right? Then there exists a number c. When it says there exists, it means that there could be more than one. There exists at least one number c somewhere in between a and b, somewhere in that interval, that when we plug that c into the function, we get the n value that you're talking about. Does that seem obvious to y'all or not, this theorem? Now, do we need continuity? Do you think continuity is important?
Yes.
Yeah, because look at that function right there. Is that function continuous? No. So if I restrict it to a closed interval like that, right? And then hold on, let's time out for a second. Sir, you weren't here last time, but everyone will attest to this. What happens if you're on your phone doing this the whole time during class? What happens? 10 points off your next exam, asked to leave, counted absent. You didn't know that because you weren't here. It's on the syllabus. I just want you to know that. Okay? Good? But I did say if you have something important, what? Take it outside. That's fine with me. All right? So I understand life happens. I just don't want that to become a habit. Okay, so we close the interval, right? Make sure the two endpoints are different. Are they different? Yes? So I should be able to find any value in between and find some value of x that goes to it. So you see in the green here, this works. But if I pick something right in here, do you see that that doesn't work? Like the function never hits that line. And the reason that didn't happen is because we didn't have the continuity. You have to have the continuity for that. So, sorry, I distracted myself. I thought there was a question. Was there a question? Someone asked me a question? No?
Well,
Yeah.
so is it right?
Are you asking me, is this right continuous?
Yes.
Here?
Where you had the endpoints.
I'm not sure. I'm not sure I understand your question.
So is the right side continuous? That right part of it?
Are you referring to that picture right there?
Yes.
Before you added.
Oh, is it continuous before I get to the little break? Are you saying, is this continuous?
It was before that.
Before that.
He's
Yes.
asking about before that, before you changed.
Oh, before I changed.
Take out that last, take out the check.
The second check.
Yes. That
There you
would,
go.
Oh,
right
that.
side, that would be right continuous.
At this particular value, it would be, yes, this would be right continuous, yes. The intermediate value theorem says you look at a function, if it's continuous, and you have to restrict it to start talking about intermediate value theorem. So start with the function, then restrict it to a closed interval, make sure the two endpoints are different, pick any number you want between those two endpoints. Guaranteed you're going to have some value of x in there that's going to get mapped to that number.
And those two endpoints are -2 and 5? Or not?
Yeah, the two endpoints here are -2, and in this case, 5. So I've guaranteed if you give me any number between -12 and 13, I'm going to be able to find a value between -2 and 5 that when I plug that into the function, it's going to spit out the number you wanted. Now, this may seem like a completely useless thing, all right? But I'm going to show you now how this is used, all right? Computer science majors? No? I know we have a few, all right? I've got 10 minutes. Don't let me go over. I'm going to show you how this is used. Show that cosine x equals x has at least one solution in the interval 0, -1. So this is going to seem like it's coming out of nowhere right now. Like all of a sudden I'm going to go try and solve an equation. Right? We've been doing limits and continuity, and now I've put an equation for us to solve, right? So this seems very not in place. But let me just follow through with this. I'm asking you to show me that equation has a solution. Some number between 0 and 1 solves that. Right now, if you start working with algebra, there's no way to solve this problem. There's nothing. You've learned nothing to solve this, and I have no algebra to solve it as well, all right? You can try if you want. I mean, what would you do? Maybe bring the x to the other side? I don't know, maybe do that? Now what? You can't factor. Divide by x if I divide by x, or I don't know, you know what I mean? Like, what am I going to do? You can sit here all day long. You can spend the rest of your life on this. You're never going to solve it, all right? You're never going to solve this. Some of you might get clever and be like, oh, I'm going to bring in the inverse cosine on the left, right? Because that's how I can get that x out of that cosine. But the problem is now you've trapped the right-hand side in the inverse cosine as well, right? If you do that on both sides. So yes, this turns into x, but now you have x's cosine inverse x. And so you still have not solved for x. In order to know x, you have to know x. So there's nothing we can do here. But the question is asking for us to show that it has at least one answer. Is it asking me for the answer? No, it's just asking me to show that there is an answer in here, right? So watch how I do this, and I have 6 minutes, 7 minutes. What I'm going to do is I'm going to bring everything to one side, okay? And now I want you to go back to college algebra, pre-cal, and think about if I ask you to find the x-intercepts of a function, what am I asking you to do? That's the y-intercept. You do what? So you set the function equal to 0, right? So would you all agree that this right here is really saying what are the x-intercepts of some function? The function I'm talking about is this one. I'm going to call it f of x is cosine x minus x. So the solutions to this equation are equivalent to the x-intercepts of this function, right? So I'm wanting to find the x-intercepts of that function. Right? That's what I want, the x-intercepts of that function. Well, check this out. Is this a continuous function? Is that continuous? Why? Is cosine continuous? Yeah, I told you that a second ago, right? All the pre-cal stuff is continuous. Is x by itself continuous? Diagonal line, yes. If you subtract two continuous functions, is it still continuous? I told you it was. You believe that, right? It's a theorem. So this should be continuous, right? It's continuous. Now, let's look at it on this closed interval 0, 1. What happens if I plug 0 into this function? What do I get? So you're going to need your calculator or no? Do you need your calculator? What's f of 0?
1.
It's 1, right? Because you just do cosine of 0 minus 0. Cosine of 0 is 1. 1 minus 0, 1, right? So here's where we are. At 0, here's what I can tell you. You're up here, right? Your graph's there. Now I'm going to plug in 1. All right, now that might be a little harder. f of 1, you do need your calculator for this. You do need your calculator, and you need to be in radian mode. What's cosine 1 minus 1? Anyone have a guess as to whether or not this answer is positive or negative? It's got to be negative. Look, cosine of 1, right? Cosine is bounded between negative 1 and 1. So biggest this could ever be is 1, and I'm taking away 1. So on your calculator, what are you getting? Negative what? Point negative. Okay, so I don't even care what it is. It's negative, yes? Okay. So do I have a continuous function? Yes. Is it defined on this closed interval? Yes, right? Where's the left endpoint? Up here at 1, which is a positive number, isn't it? And then I get over here to this, and now I'm down here at a negative number. And since it's continuous, it's got to go from here to here, and I can't pick up my pencil, which means somewhere in there, I've got to do what? Cross. Do I know where it is? No, but I know it's there, right? And that's what this was asking me to do. Show that it has at least one answer. There, I've shown it. So how did I show it? I just want to back up. How did I show it? I showed it by turning the equation into a function's x-intercepts, confirming that that function's continuous, showing that at the left endpoint and right endpoint we had a what?
Continuous, and then it passes through the x-intercept.
How did I know it passed through the x though? Because it went from what? Positive to negative. Had it gone from negative to positive, I'd still know that, wouldn't I? So I showed a change in sign. With me? I still don't know the answer, do I?
No.
So do you think it would be easy to program a computer to take this expression and plug in 0 and plug in 1 and give you two answers? Do you think you could program a computer to do that pretty easily? Like here's this function, plug in 0, then plug in 1. It could do that pretty quick, pretty fast, yes? And then it would say, okay, one of them's positive, one of them's negative. So it would say somewhere in between there is 0. So now what I would have that computer do is this. I would have it cut this interval in half. And instead of looking between 0 and 1, I'm now going to look between 1/2. Well, let's start here. Let's go 0 to 1/2. Let's look in here. So whoever's got their calculator, we already know what happens at 0. Plug in 1/2. Oh, plug in 1/2, and what do you get? All I care about is if it's positive or negative.
0.3, it's positive.
It's positive, right? Okay, so it's positive. So that tells me this, that I'm going from positive to negative between here and here, which means my answer, I know it a little better now. Where is it? Between 1/2 and 1. So what could I now tell my computer to do again? Abort? Oh, did I hear? Oh, you said 3/4. I thought you said abort. Okay, abort mission. Okay, so I would go halfway between there and there, right? And I would check it 3/4. Do you want to try it for me? Do 0.75 or 3/4. Tell me what you get.